Welcome back to ECE 320A. In this video, I'm going to be working through a little bit of a review, and in particular, some problems dealing with exam number 4. And the first problem that we're looking at is examining the phase behavior of a particular transfer function at low frequencies and high frequencies. And really the first thing that you probably want to do is identify where your poles and zeros are located. In this particular case, excuse me, your transfer function is already in factored pole zero form. If it was not, if you had quadratic factors, then you would need to find the roots of those quadratic factors and determine if they are real or complex. But here you can see that we actually have, in this transfer function, a 0 at the origin. We also have a 0 at s equal minus 5. We have two poles at s equal minus 1 and a pole at s equal minus 10. And we'll now need to figure out how do we use that information. In this particular problem, it's asking us to find the phase of h of j omega at low frequencies and find the phase of h of j omega at high frequencies. At low frequencies, if we didn't have this 0 at the origin, what do we mean by low frequencies? That 0 at the origin is always active, so that's happening at low frequencies. But let's just, for now, say that we don't have a 0 at the origin. What would we consider low frequency? Well, in this case, since we're talking about phase, we need to be worrying about a decade below and even further below that to consider something low from the smallest frequency of interest or that's in your system. In this particular case, we actually have a pole at omega equal to 1, and we would then want to be a decade below that, so low frequencies would actually mean something omega less than a decade below 1, so something below 0.1 would be low frequency. That's what we would mean by low frequency. And what we mean by high frequency is really after every pole and zero has contributed its phase or introduced and fulfilled all of its phase contribution. That means that for high frequencies, we need to be more than a decade beyond the highest frequency. In this case, we have omega equal to 10 as our highest pole, so our high frequency terminology would mean that we were looking at omegas bigger than a decade beyond 10, which would say, oh, high frequencies mean we need to worry about omega bigger than 100. So that's what we're meaning by low frequencies and high frequencies in these problems. Let's now see if I can judiciously erase some of this information and now try to solve the problems. What's the phase at low frequencies? Well, now in this particular case, we do actually have a 0 at the origin. That's going to be active at low frequencies. And what does a single 0 contribute in terms of phase? It's in the numerator. It's always on, so that phase at low frequencies in this transfer function is going to be at low frequencies only from the 0 at the origin, and that's going to be giving us 90 degrees. So the phase at low frequencies, let's say theta sub A, is going to be plus 90 degrees. That's the answer to problem A, or part A of problem 1. Part B of problem 1, what's the phase at high frequencies? Now we're interested in everything that's already contributed all of its phase. All of these factors have to have contributed their phase. So in this case, we have 2 zeros net, and we have 1, 2, 3 poles. And at high frequencies, we're really interested in this pole zero excess, or how many more poles do we have than zeros. In this case, we actually have one more pole than zero, meaning at high frequencies, this H of S is looking like a 1 over S. And so at high frequencies, the phase, theta sub B, is going to be, since we have more poles than zeros, the phase due to poles is downstairs, that's negative, and we only have one of those. And so the answer to part B of this problem, and maybe this will be confusing, so let me erase that, but the phase at high frequencies for this particular transfer function is minus 90 degrees. And that's how you could determine it. Just look at the pole zero excess. If you had a pole zero excess of 2, then your phase at high frequency would be 2 times minus 90, or minus 180 degrees. If you had a pole at the origin instead of a 0 at the origin, then we would have an angle of minus 90 degrees at low frequencies. That's now problem number 1, which was dealing with phase. Problem number 2 is interested in the magnitude, or the slope of that magnitude. In this particular case, it looks like we do have a different transfer function. We have a pole at the origin, and that's really what we want to be focusing on. Do we have, at low frequencies, do we have any poles or zeros at the origin? Poles are always sloping down, and we just have one pole at the origin, and it's going down at minus 20 dB per decade since it's 1. And that means then that the slope of this transfer function is impacted only by that single pole at low frequencies. And so the slope, I don't know how I want to designate that. Maybe I just say S for part A is now minus 20 dB per decade. If we did not have any poles or zeros at the origin, then at low frequencies, which is less than a decade before any of the poles or zeros even break, actually it's before they break, so a decade before doesn't really have to worry so much when we're talking about the magnitude. But if we didn't have a pole at the origin or a zero at the origin, we would be at 0 dB flat, and it wouldn't be sloping, meaning the slope at low frequencies could be 0 dB per decade. But in this case, our answer for this particular transfer function is minus 20 dB per decade. And what's the slope at high frequencies? Again, when we're at high frequencies, we're assuming all of the poles and zeros have broken or been introduced, and in this case, everything is going to have been introduced into the frequency response after omega equal to 10, and we have 3 poles and 1 zero in this particular problem. So our pole zero excess is equal to 3 minus 1, which is 2. So effectively, at high frequencies, this transfer function looks like 2 poles. If we have 2 poles, 2 real poles, they're each sloping at minus 20 dB per decade. So the slope for part B at high frequencies is now 2 times minus 20, or minus 40 dB per decade. And that's the answers then to problems 1 and 2 on exam number 4. And what you could do, just for practice, is you could start to think about what do these frequency responses actually look like. But if you were plotting the frequency response for these transfer functions, at least now you have a way of checking your low frequency starting position and your high frequency ending position or the slope at low frequencies and high frequencies if you're dealing with transfer function magnitude. But you could, if you wanted to, start looking at the magnitude response of, let's say, transfer function in problem 2. And you can quickly start to see that. We have a pole at the origin, which will be producing a slope. Then what do we hit next? Well, then we hit a 0 at omega equal to 1. And then we hit 2 poles at omega equal to 10. So we won't be going down at minus 20, but we'll be going down at minus 40 dB beyond omega equal to 10. And where this is, up and down wise, depends on the gain, and we would have to then factor this or put this in time constant form to find the gain. But I think you can see that we have 100 downstairs, we have 100 upstairs, so the absolute gain is 1 in dB terms. That's 0 dB, so we really don't even have to shift this up or down in this particular case. And the slope here is minus 20 dB per decade. This one is minus 40 dB per decade because of those 2 poles at omega equal to 10. And that's now a very quick sketch of the magnitude behavior of this transfer function, and it should be consistent with your answers for part A and part B of problem number 2. And you could do the same thing with the phase. The phase is now starting at 90 degrees, and then it starts to change a decade before the next break, and that break is at 1. So at 0.1 we start going down, but we're going down with the influence of 2 pole factors. So we're going down at minus 42 times minus 45 degrees per decade. So we're going down at minus 90 degrees per decade. Then we actually hit a 0 at 0.5 a decade before its break frequency, and that now causes our slope to be not quite as severe. It's now minus 45 degrees per decade because that one has now helped reduce the minus 90 to, well, the zeros contributing plus 45 degrees per decade. And all of these now start and stop. When is this particular contribution going to finish? It's going to finish a decade beyond 1, so it will turn off at 10. This one will turn off at 50. This one will start turning on at 1 and turning off at 100. And so you can see that these bends and kinks in your phase curve are going to be going up and down a little bit more dramatically than the magnitude. But I will leave that to our Bode plot problem, but that's giving you then a hint as to why you might be interested in this low frequency and high frequency behavior of your phase and your magnitude.